The purpose of this presentation is to, in some way, answer the question, what drives an endothermic process? The fact that a reaction can proceed and increase the bond energy, the chemical potential energy, is in itself a fascinating question. You come from physics class, and what do? You set the cart at the top of the ramp, you let the cart go, it goes down the ramp. Watching a system convert potential energy to kinetic energy seems reasonable. Or you pull on a spring to give the spring stored potential energy. You let go, you release the spring collapses, if you will, moving that potential energy to kinetic energy. But in chemistry, we do have the reaction and we do have the process in which you have lower potential energy to start, and as the reaction proceeds, the reaction obtains higher chemical potential energy. That's reactants and that's products there. Okay, so that's the question we're looking to answer. We won't do it for chemical reactions, but we will do it for an endothermic process, and that's going to be the evaporation of water. The evaporation of water. So we study that in chemistry. It is not technically a chemical process. We don't have fundamental rearrangement of the atoms of the water molecules, as you saw in that earlier video I had you watch. But it is a chemistry process, if you will, and it has an equation. So what we have there is we have water, and its state symbol is liquid as a reactant, and the product, if you will, of the process is H2O in the gaseous phase. Okay, so if that's the equation for the process of evaporation, water going from liquid to gas, it also happens to be the equation for the process of boiling. And we're very familiar with that, but you can use these diagrams to defend that this process here of liquid water to gaseous water is endothermic. It requires energy. Now, the visual that you see in there is you're actively supplying the energy. So, but it still gives us the impression, or it still defends the comment that water going from liquid to gaseous phase is endothermic. Energy has to be added to the system in order to get it to occur. And here I'm just making the connection between your kitchen experience and the chemistry lab experience. So there's a lot of crossover in that. Going to page 2. Okay, this was an image from a video that you watched, and I thought he did a nice job with talking about the speed of the molecules. So I'm going to edit these a little bit to put in the speed. So what he mentioned is that in order for water to evaporate, you have to have that molecule that's moving fast. I want to change that to pen. You have to have that molecule that's moving fast at the surface. And if it gets, right, all these water molecules are striking each other or colliding with each other, as was mentioned in the video I had you watch. So if you have the water molecule that's moving fast and it just gets hit in the right way and it's already at the surface, then it has that ability to escape the liquid phase, if you will, and go into the vapor phase. It remains an H2O particle, but it's now H2O gaseous. Now, I'm going to come back to this drawing in just a second, but I do want to give you one more piece of background information that is needed in order to defend the evaporation of water, or to take you through the steps of the evaporation of water being an endothermic process. So we've talked about a thermometer measuring temperature, and that temperature is a measure of the average kinetic energy of the particles of the system. Well, in one way, it's a measure of the average kinetic energy of the particles of the system, is that for any temperature, you do have particles that are moving a little faster than average, and you do have particles that are moving a little slower than average. So just because we say a system is at 25 degrees Celsius, and then we find out it's water, and we can figure out the mass of water, and we can do some calculations to figure out the speed of a water molecule that's at 25 Celsius. That doesn't mean they're all obeying that. It means on average they're obeying that. But there are water molecules, so on average they're obeying that, but there are water molecules that are moving, this x-axis is velocity. There are water molecules that are moving quite faster than that. Any of these up here are moving quite faster than that. And there are water molecules that are moving slower than that. So I come back to this diagram and I want to edit it a little bit in terms of showing that there are particles that are moving faster than the calculated speed based on the temperature of the system, and there are particles moving slower. So I'm going to draw a shorter arrow. There are faster particles, but they're beneath the surface, so they don't have a chance to escape the liquid to the gas. And there are slower moving water molecules at the surface. So the ones that are going to escape the liquid and become the gas are the ones that are moving faster at the surface. And so evaporation doesn't happen instantly, it happens over time, as, again, that lucky water molecule, if you will, just happens to be at the liquid gaseous surface, and it happens to have the right collision in the right way, and it's moving a little faster than average, and boom, it leaves the liquid and becomes a gas. So this piece right here is something I'd like to be able to ask you about a little bit, and that's the student understanding that just because we say the temperature of the system is 25 Celsius or whatever temperature you pick, that doesn't mean that all the particles are moving at exactly the same temperature, at exactly the same speed. So temperature is a measure of the average speed of the particles in the system, but there are some that move higher and some that move lower than average. All right, I see that I'm at 7 minutes, but I just have this one page to go. So I'm going to keep going here. So now I've got to get to the part that says, well, it's endothermic. And so I'm going to come back to this where I have the container. I'm going to make it a container now. And I'm going to remind us that we've had some faster water molecules escape over time. So that one, a lucky one, moving faster at the surface, got struck the right way by its neighbors, boom, it's gone. And then a few minutes later, this one moving faster than average at the surface, got struck the right way by its neighbors, boom, it's gone. And so now we have this lower image here, and that shows some of the water molecules that have left. Well, this is critical understanding for the process number 2, if you will. If the higher velocity molecules have escaped, well, then what that means is that there are just the lower velocity particles and some higher velocity particles that were not at the surface. But the ones that have escaped are the higher velocity particles. So that means the temperature of this has now dropped. The temperature of the liquid is now lower. Temp of liquid now lower. So if this whole container of water was at room temperature and now the temperature is lower, well, what happens is you have heat energy enter the system. I should draw my container boundary again. But you see what this one is I showed a few of the water molecules leaving. Now obviously water seeks its own level, it would all be flat again, but the idea is now that the water has at a very small amount lowered its temperature and it's in a room temperature environment, now heat energy transfers into that system of water and warms it back up again. And then as it becomes warmer, it increases the average speed of the molecules, and now you can continue the process again of getting those water molecules that happen to have a high enough speed, they happen to be at the surface, and they're going to go from a liquid to gas. And again, this is happening at very small time increments and temperature increments, but then the temperature of that water cools as a result of the higher velocity particles leaving. And then you have more heat come in and it warms the remaining water back up, and then the process can continue to repeat until you don't have any water left. The book calls this matter spread. Now, I'm not going to have you read that part of the book, but just like if we had a bottle of perfume or cologne in the class and we were in the corner and someone squirted a little bit, over time those particles would undergo matter spread, and those in the back of the room could even start to smell it, smell the perfume or cologne. The same thing is happening here, that this matter spread is a driving force, if you will. So that's the extent to which the book takes it. I'm not going to have you read the book part of matter spread, but I do want you to understand evaporation is an endothermic process and be able to go through some of the steps that I've outlined here. Thank you.